Hi, I'm Sean Gannon, and this is Minute Math, and today we're learning about exponential equations not requiring logarithms.
Minute Math, when you need help you use Minute Math.
We're given this problem right here, 4 to the 2x plus 3 power, and that is equal to 1, and we have to solve this. So I want to find a way to have the same base for both sides of this equal sign. This one is the tricky part, but remember, anything to the 0 power is equal to 1. So we can take this 4 to the 2x plus 3, and I can rewrite this to be 4 to the 0 power. With that being said, we now can set just the exponents equal to each other and solve for x here, since the base is the same. So now we have a 2x plus 3 equals 0, and this is a pretty easy problem to solve. Subtract a 3 to both sides, and we have 2x equals a negative 3. Divide both sides by 2, and x equals a good old negative 3/2, and that is our final answer. We're given this problem right here, 5 to the 3 minus 2x power equals 5 to the negative x power, and we have to solve this equation. Well, notice we have the same base here of 5. When that happens, we just have to worry about the exponent. So we can set the exponents just equal to each other now. 3 minus 2x is equal to a negative x. Now we solve for x. Pretty easy, actually. Add a 2x to both sides. If I can write an x, 2x's cancel, and we have a 3 on the left, and negative x plus a 2x is just a 1x. So if you want to rewrite it x first, x equals 3, and that is our final answer. We're given this problem right here, 3 to the 1 minus 2x power is equal to 243, and we need to solve this equation. Well, first thing is I want to have the same base here, okay, for both sides of the equal sign. 3 I can't really do anything with, but 243 I can. So I'll rewrite the left-hand side, 3 to the 1 minus 2x power. And 243 is the same thing as 3 to the 5th power. When this happens, we can take, well, we know the same base is now 3. We can take the exponents and set them equal to each other, and then we solve. So I have a 1 minus 2x equals 5, and let's solve for x here. Well, I'm going to subtract a 1 to both sides here, and I have a negative 2x equals 5 minus 1, 4. Divide both sides by a negative 2, and not too shabby. X is completely by itself. 4 divided by a negative 2 is a negative 2. And so my final answer here is just x equals a negative 2. We're given this problem right here, 3 to the 2a power equals 3 to the negative a power, and we have to solve this equation. Well, our base is the same here with both being 3. So with that being said, we can take the exponents and set them equal to each other and solve. So we take a 2a equals a negative a, and then we're solving here. Okay. Now this is a little tricky. We have a negative a and a 2a. To bring that a over to the left-hand side to combine our like terms, I'm actually going to add an a to both sides. 2a plus 1a is a 3a, and negative a plus an a is a 0. From there, I divide both sides by 3, and a is equal to 0 divided by 3, which is 0. And so my final answer here is a equals 0. We're given this problem right here, 4 to the 3x minus 2 power, and that's equal to 1, and we have to solve this equation. What's tricky here is when we're setting these up, we want to have the same base on both sides of the equal sign. In this case, it's going to be the 4. So how can we convert this 1 to be a 4? We can do so by knowing that 1 is the same thing as 4 to the 0 power. So we take the information on the left, 4 to the 3x minus 2, and now we have an equal sign here with a little expression on either side, both of the same base as 4, and it's raised to some exponent. When that happens, we can take the exponents and set them equal to each other. So we take a 3x minus 2 and set it equal to 0, and we solve for x. We add a 2 to both sides, and we have 3x now equals a positive 2. Divide both sides by 3, and x equals a positive 2/3, and that is our final answer. We're given this problem right here. 4 to the 2p power equals 4 to the negative 2p minus 1, and we want to solve this equation. Luckily, we already have the same base here of 4. When that happens, we just look to the exponents. We can take our exponents, 2p, and set it equal to a negative 2p minus 1, and now we just solve for p. I add a 2p to both sides as combine our like terms. 2p plus 2p is a 4p, and that's equal to that negative 1 left over. Divide both sides by 4, and p equals a negative 1/4, and that is our final answer. We're given this problem right here. 6 to the negative 2a power is equal to 6 to the 2 minus 3a power, and we need to solve this equation. Luckily, we have the same base, which is 6 here. And when that happens, that's the only thing on each side of the equal sign, we can look to the exponents. We can take each one of these exponents and set them equal to each other. So negative 2a now is equal to 2 minus 3a, and we're solving for a. I'm going to add a 3a to both sides, and this is actually over fairly quickly. Negative 2a plus a 3a is just a 1a, which we can write just as a. A 2 is what is left over, and that's it. Our final answer here is a equals 2. We're given this problem right here, 2 to the 2x plus 2 power, and that's equal to 2 to the 3x power, and we have to solve this equation. We have the same base for each one here on each side of the equal sign, and that base is 2. And it's being raised to some exponent. But when that happens, we can pretty much ignore the 2 now and just set the exponents equal to each other. 2x plus 2 is equal to a 3x. And now we're solving for x. We subtracted 2x to both sides, combine our like terms, and 2 is just left over on the left-hand side, and on the right-hand side, 3x minus 2x is just a 1x. Flip that over, make it easier to see, and x equals 2, and that is our final answer. We're given this problem right here. 6 to the 3m power times 6 to the negative m power equals 6 to the negative 2m power, and we need to solve this equation. Well, what's tricky here is we have this multiplication going on, but luckily we have the same base, which is 6. When that happens, we look to the exponents. We can rewrite this to be 6 to the power of 3m plus, because it's multiplication here, a negative m, and that's equal to 6 to the negative 2m power. Now we have on each side of the equal sign the same base of 6, and it's being raised to some exponent. When that happens, we can take our exponents and set them equal to each other. 3m plus a negative m is equal to a negative 2m. Combine our like terms on the left-hand side. 3m plus a negative m is a positive 2m. We minus a 2m here. I'm going to add a 2m to both sides. Right-hand side is a 0. Left-hand side, 2m plus a 2m is a 4m. Divide both sides by 4 to get m completely by itself, and well, 0 divided by 4 is a 0. And so my final answer here is m equals 0. We're given this problem right here, 2 to the x power divided by 2 to the x power, and that's equal to 2 to the negative 2x power, and we have to solve this equation. Well, our rules with dividing problems here, or dividing with same base, and the exponents right here, right? If we have the same base, we subtract the exponent. Took me a while to get that out there. But it's 2 to the x, the first exponent, minus the x. So we subtract the exponents here when the bases are the same. The right-hand side stays the same, of 2 to the negative 2x power. Well, x minus x is just 0. So we have 2 to the 0 power equals 2 to the negative 2x power. Now again, when we have the same base on either side of the equal sign, we can set the exponents equal to each other. 0 now equals a negative 2x, and I solve for x, divide both sides by a negative 2. And I have 0 divided by negative 2, 0, is equal to x. So I can rewrite it here as just x equals 0, and that is our final answer. We're given this problem right here, 10 to the negative 3x power times 10 to the x power, and that's equal to 1 over 10. And we have to solve this. Well, first thing, when I have the same base going on right here, which is 10, and I'm multiplying them, I can rewrite this to be 1 base of 10, and I take the exponents and I add them. Negative 3x plus that x right there. And that's equal to, and I'm going to write this now with a 10 as my base, and to do that, I can put a negative 1 power here. 10 to the negative 1 power, it's the same thing as 1 over 10 to first power. From there, we can, well, simplify a little bit here. Negative 3x plus x is a negative 2x. So we have 10 to the negative 2x power is equal to 10 to the negative 1. Now, we have the same base, which is 10. When that happens on either side of the equal sign, we can take our exponents and set them equal to each other. So we have a negative 2x, if I can write it here, is equal to a negative 1. Now we solve for x. Divide both sides by a negative 2, and x equals negative 1 divided by, that's a negative 2 right here, is a positive 1/2. And so my final answer here is x equals a 1/2. We're given this problem right here, 3 to the negative 2x plus 1 power times 3 to the negative 2x minus 3 power is equal to 3 to the negative x power. And we have to solve this equation. Well, first thing I notice is that we have the same base here, 3 and a 3, and it's being multiplied. When that happens, we add the exponents and keep the same base. So we have 3 now to the negative 2x plus 1 power plus negative 2x minus 3 power. And that's just going to be equal to 3 to the negative x power. Now we have the same base to a crazy exponent here, but it's equal to the same base of 3 to a negative x power for the exponent. When we have that with the same base, we can just set the exponents equal to each other. So negative 2x plus 1 plus a negative 2x minus 3 is now equal to a negative x. Let's combine our like terms. Negative 2x and a negative 2x is a negative 4x. 1 plus a negative 3 is a negative 2. And that's equal to a negative x. I'm going to add a 1x to both sides, and I'm going to add a 2 to both sides. Let's bring our numbers to the right and our variables to the left. Negative 4x plus 1x is a negative 3x, and these 2's cancel. These x's cancel, and we just have a positive 2 on the right. Divide both sides by a negative 3, and x equals, well, a negative 2/3, and that is our final answer. We're given this problem right here. 4 to the negative 2x power times 4 to the x power equals a 64, and we want to solve this equation. Well, notice this multiplication that's going on right here between the 4 and the 4. Now they have exponents, but we have the same base. When this happens, we can combine this to be one part with a base of 4, and we take the exponents, the 2x and the x, and we add them together. So we combine them to be one base, but we add the exponents when it's multiplication. Now the 64, I'm going to rewrite this with, well, a base of 4. 64 is the same thing as 4 to the 3rd power. Now we have 4 and a 4. We have the same base on either side of the equal sign. When that happens, we can set the exponents equal to each other and solve. So we have a negative 2x now plus an x from the left, and on the right is just a 3. And let's solve for x. Negative 2x plus 1x is negative 1x, and we have a 3. Divide both sides by a negative 1, and it's pretty easy. X equals, well, 3 divided by negative 1 is a negative 3. So my final answer here is x equals a negative 3. We're given this problem right here, 6 to the negative 2x power times 6 to the negative x power, and that's equal to 1 over 216. And we have to solve this. Well, our rules state we have multiplication here, and we have the same base. When that happens, we keep the same base if we want to combine it to be one part here, and we add the exponents, negative 2x plus a negative x. You see how they come down here. Now the right-hand side, I'm going to see if I can rewrite this to be something with a 6 with an exponent. 6 to the 3rd power, is 216. So 6 to the negative 3rd power is equal to 1 over 216. We now have the same base here. And when we have that over equal sign, we can set the exponents now equal to each other. We take a negative 2x now plus a negative 1x, and it's equal to that negative 3. Well, negative 2x plus a negative 1x is a negative 3x, and it's equal to a negative 3. Solving for x, divide both sides by a negative 3. And x equals negative 3 divided by negative 3 is a positive 1. And so my final answer here is x equals a positive 1. We're given this problem right here. 2 to the x power times 1 over 32 is equal to 32. And we have to solve this. Well, one thing I know about 32 is that I can write that to be 2 to the 5th power. And that's going to be the name of the game here. We want to write everything we can with a base of 2. So if 2 to the 5th power is 32, then 2 to the negative 5th power is 1 over 32, and then 2 to the x just comes down. Well, now we have 2 and a 2 being multiplied, and they have different exponents here. When that happens, if we want to write it as a single base of 2, we add the exponents. So we have 2 to the x plus a negative 5 for the exponent. That's equal to, well, 2 to the 5th power right here. Now, our rules also tell us when we have the same base on either side of the equal sign, we can set the exponents equal to each other. We have x plus a negative 5 now, or minus 5, and it's equal to a positive 5 on the right. To get rid of that 5 and bring it over, I add a 5 to both sides. These 5 cancels. I have an x over here, and 5 plus 5 is 10. And that's it. Our final answer here is x equals 10. We're given this problem right here. 2 to the negative 3p power times 2 to the 2p power is equal to 2 to the 2p power, and we want to solve this equation. Our rules about exponents here is when they have a same base here being multiplied, we can combine it with a single base, which is 2 here, and all we have to do is add the exponents. So negative 3p plus a 2p here. And that's going to be equal to the right-hand side, 2 to the 2p power. Now they also tell us when we have the same base here on either side of the equal sign, we can just set the exponents equal to each other. So negative 3p plus a 2p is equal to a 2p. From there, we solve for p. Negative 3p plus a 2p is a negative 1p, and that's equal to a 2p right here. I subtract a 2p to both sides. Negative p minus a 2p is a negative 3p, and the right-hand side is just 0. Be careful here. We divide by a negative 3 to both sides, and p is now by itself. I'll put it up here. P is now by itself, and 0 divided by negative 3 is a 0. And so my final answer here is p equals 0. We're given this problem right here. 64 times 16 to the negative 3x power is equal to 16 to the 3x minus 2 power, and we want to solve this equation. Well, we want to see if we can find a common base for each little section here. And what's difficult is 64 I can't really write in terms of 16. But what I can do here is, I know 64 is, well, that's 4 to the 3rd power. And 16 is 4 squared. But I still have to raise that to the negative 3x power. Same with this 16 is a 4 squared. And then it's a 3x minus 2 power right there. So what can we do with that? Well, we can keep going down and know our rules of raising something to another exponent and how that applies is with multiplication. So we have 4 to the 3rd power times 4 to the 2 times the negative 3x power now in that exponent. And the same thing here, 4 to the 2 power times the 3x minus 2 right there. We keep on going. Our rules state that if we have the same base and we're multiplying, we add the exponents. So to write this as one big base of 4, it would be 4 to the 3 plus a 2 times a negative 3x as such. And that's equal to, again, 4 to the 2 times 3x minus 2 power. We now have the same base of 4 on each side of the equal sign, so we can set the exponents equal to each other, and then we solve. So we have 3 plus a, well, 2 times the negative 3x, let's get that out of the way, it's a negative 6x here. And then 2 times the 3x is a 6x, and 2 times the negative 2 is a minus of 4. And so let's go combine our like terms here. I'm going to add a 6x to both sides. I'm going to add a 4 to both sides. 4 plus 3 is a 7. The 6x's cancel. And 6x plus 6x is a 12x. And the 4's cancel. I divide both sides by 12. And I can rewrite this up here with x by itself here. And all the 12's cancel. And so x equals 7 over 12. And that is, our final answer. We're given this problem right here. 81 to the 3n minus 2 power over 243 to the negative n power. That's equal to 3 to the 4th power. And we got to solve this. Well, 81 and 243 I can write in some form of 3. What does that mean? Well, 81 is the same thing as 3 to the 4th power. So I'm going to do that, but keep my exponent of 3n plus 2 there. 243 is 3 to the 5th power, and I still have my negative n for the exponent. And 3 to the 4th power is still there. Our rules of exponents now state when we have something, or 3 to an exponent here, raised to another exponent, we multiply the exponents there. So we would have now 3 to the 4 times 3n plus 2 power over, same thing here, 3 to the 5 times a negative n, and that's equal to 3 to the 4th power there. Continuing on over here, all right, our rules of division when we have the same base as we subtract the exponents. So I have a 3 to the 4 times 3n plus 2 power minus the 5 times a negative n right there, all right, and that's equal to 3 to the 4th power right there on the right hand side. Keep on going. We have the same base here. It's a big exponent up here, but we have the same base. When that happens, we can set the exponents equal to each other. And while we do that, let's simplify this a little bit. 4 times 3n is a 12n, and 4 times a 2 is an 8. And we have, well, 5 times a negative n is a negative 5n, but the double negative makes it a positive. Plus 5n, and now that's equal to just that 4 being the exponent. Combine our like terms, subtract an 8 to both sides here. And 12n plus a 5n is a 17n. And 4 minus an 8 is a negative 4. I divide both sides by 17, and n is now completely by itself, and this doesn't simplify anymore. So we have negative 4 over 17, and that is our final answer. We're given this problem right here. 81 times 9 to the negative 2b minus 2 equals 27, and we want to solve this equation. Well, each one of these, the 81, the 9, and the 27, can be written as 3 to some power. 81 is 3 to the 4th power, 9 is 3 squared, but keep the rest, negative 2b minus 2 in the exponent, and 27 is 3 to the 3rd power. That's going to be important soon. Now, simplifying here, the 3 to the 4th power stays there, but our rules state when we raise something that's an exponent to another exponent, we multiply the exponents. So this is 3 to the 2 power times a negative 2b minus 2. And that's equal to 3 to the 3rd power. All right. We now have the same base of 3, and it's being multiplied. And in our rules state we add the exponents if we want to keep that same base of 3. So 3 here now is to the power of 4 plus 2, and I'm going to rewrite this actually. Let's go all the way out. 2 times a negative 2b minus 2 here, and that's equal to 3 to the 3rd power. From there, we have our bases of 3 on each side of the equal sign. So when that happens, we can just set the exponents equal to each other and solve. 4 plus 2 times a negative 2b minus 2 is equal to that exponent of 3. Now let's finish solving it up here. We're going to solve for b. So 4 stays there, plus, let's distribute this 2 across. 2 times a negative 2b is a negative 4b, and 2 times a negative 2 is a negative 4. And that's equal to just that good old 3. We want to combine our like terms. 4 and a negative 4 added is just a 0. Don't need to write that, so they cancel each other out. We have a negative 4b now is equal to just a 3. Divide both sides by a -4, and b is now by itself, and it's equal to a -3/4, and that is our final answer. We're given this problem right here, 9 to the -3x power times 9 to the x power, and that's equal to 27, and we need to solve this equation. Now, I notice we don't have the same base all the way around. But what I can do is rewrite each one of these with the same base in a way. 9 is the same thing as 3 squared, and that's the -3x power. Do the same thing here, multiplied by a 3 squared to the x power, and 27 is 3 to the third power. Now our rules with exponents and raising something to another exponent is that we can keep that base of 3, but we take these exponents and we multiply them. So 2 times a -3x is a -6x right here. Same thing here, 3 to the 2 times x is a 2x power. And that's equal to 3 to the third power. Now our rules also tell us when we have the same base being multiplied, we just add the exponents when we combine them. So this is now 3 to the -6x plus a 2x. That's equal to 3 to the third power. Now we have the same base again on either side of the equal sign. With that, we can just set the exponents equal to each other and solve. So we have a -6x plus a 2x equals a 3, and let's go solve for x. Well, -6x plus a 2x is a -4x. That's equal to 3. Divide both sides by a -4, and x equals, I'll put it right here, x equals a -3/4. And that is our final answer. We're given this problem right here, 1/6 to the 3x plus 2 power times 216 to the 3x power, and that's equal to 1/216, and we need to solve this equation. Well, what I try to do here is I want to find a same base number raised to an exponent that can kind of give me a good base here. Not really meant to say that, but how it's said, but it is. Well, 6 to the -1 power is 1/6. So I can write this as 6 to the -1 power to 3x plus 2. Multiplied by 216 is the same thing as 6 to the third power. We're still raising that to 3x. Since 216 is 6 to the third, 6 to the -3rd is the same as 1/216. And now we have like 6's going across the board, so this is going to help us here. So let's simplify where we can. Our rules of exponents say when we have something raised to an exponent and then raise it again, we can keep that same base, which is 6 here, and multiply the exponents. So we have 6 here to the, let's distribute, multiply that -1. -1 times 3x is a -3x, and 1 times 2 is a -2, or -2. Same thing here, 6 to the 3 times a 3x is a 9x. And that's equal to 6 to the -3rd power. Keep that to the right. Our rules also state that when we have multiplication with the same base, we add the exponents and we can keep the same base here of 6. So -3x now minus 2 plus that 9x is the whole exponent here for the 6. And that's equal to 6 to -3. Our last exponent rules. We have a 6 in the denominator. It's on both sides, or not denominator, in the base, and it's both sides of the equal sign. When that happens, we can set the exponents equal to each other. -3x minus 2 plus a 9x is equal to -3, and from here we can solve for x. Let's do that up here. Let me add a 2 to both sides. Okay, not forget that. -3x plus a 9x is a 6x right here. Add a 2 to both sides, that cancels. -3 plus 2 is a -1. Keep on going, divide both sides by a 6, and x equals a -1/6. And that is our final answer. We're given this problem right here, 243 to the k plus 2 power times 9 to the 2k minus 1 power, and that's equal to 9, and we need to solve this equation. Well, 243 and 9 all share a common thing, that they're divisible by 3. So let me go, or a power of 3 actually, more specifically. 243 is the same thing as 3 to the 5th power. So replace that, but still raise it to the k plus 2 power. 9 is the same thing as 3 squared, and we still have a 2k minus 1 in the exponent. And then we have a 9 on the right. From here then, we have to use our rules with exponents to try to simplify this a little bit. When we have 3 to the 5th power raised to the k plus 2 power, we multiply the exponents and we keep the base of 3. 5 times k is a 5k, and 5 times 2 is a 10. Multiply it out, same idea. 3 is the base, 2 times 2k is a 4k, and 2 times a minus 1 is a negative 2. And that's equal to, I forgot to do it with the 9 here, but 9 being 3 squared. If you realize that I forgot to do that here to this 9, let me know down in the comment section below. Well, from here, we have the same base again being multiplied. When that happens, we add the exponents. So we have 3 to the 5k plus 10 now, plus a 4k minus 2 in the exponent. That's equal to 3 to the 2 power. A lot of work here. All right. Our rules also state that when we have a base to a big exponent and a base to an exponent and it's equal to each other, we can just set the exponents equal to each other. All right. So this exponent of 5k plus 10 plus the 4k minus 2 is equal to just this 2 right here. And now we can solve for k. 5k and a 4k is a 9k, combine our like terms. 10 minus a 2 is a positive 8 equals a 2. Subtract an 8 to both sides, and I'll write this up here. We have a 9k here is now equal to 2 minus 8, which is a negative 6. Divide both sides by 9, and k equals negative 6 divided by 9, which is the same thing as negative 2/3. And so my final answer here is k equals a negative 2/3. We're given this problem right here, 16 to the r power times 64 to the 3 minus 3r power is equal to 64, and we have to solve this equation. Now, one thing I want to do is find each one of these 16 and 64 something I can write with the same base raised to an exponent. And that's going to be 4. 4 squared is 16, but we still raise it to an r power. 4 to the 3rd power is 64, and we still have to raise that to the 3 minus 3r power. And again, 64 is 4 to the 3rd power. Now our rules when we have the same base here, right? We have a base to an exponent, and as raised to another exponent, we multiply the exponents. So we have 4 to the 2r now, 2 times r, times 4 distribute here. 3 times 3 is a 9, and 3 times a minus 3r is a minus 9r. Oof. And we have 4 to the 3rd power here. Now with multiplication with the same base here, we add the exponents and keep it the same base. So 4 to the 2r plus 9 minus 9r is equal to 4 to the 3rd power. Now we have the same base again with 4 over an equal sign. All these exponent rules. When that happens, we just set the exponent equal to each other, or we're allowed to. So we have 2r plus 9 minus 9r is equal to a 3. From here, we need to solve for r. I subtract a 9 to both sides here to get our like terms together, and 2r plus a negative 9r, or minus 9r, is a minus 7r, and that's equal to 3 minus 9, which is a minus 6. Keep on going here, divide both sides by negative 7, and r is equal to negative 6 divided by negative 7, which is a positive 6 over 7, and that's it. It doesn't simplify anymore, and so our final answer here is r equals 6 over 7. We're given this problem right here, 16 to the 2p minus 3 power times 4 to the negative 2p power is equal to 2 to the 4th power, and we need to solve this equation. Well, I want to see if I can rewrite the 16, the 4, and then not really the 2 because it's already like that, but 16 to the 4 with the power of 2 being in a base here of 2. Well, 16 is 2 to the 4th power, and we still raise that to the 2p minus 3 power. 4 is, well, 2 squared, and it's still raised to the negative 2p power, and then we have 2 to the 4th power still here. Now our rules here with exponents state that if we have 2 to the 4th power, all raised to the 2p minus 3 power, we multiply these two exponents. So 4 times a 2p is an 8p, and 4 times a minus 3 is a minus 12. Same thing here, this 2 base comes down, multiply 2 times the negative 2p, and we have negative 4p right here, and that's equal to 2 to the 4th power. Our rules also state that when we have the same base as 2 being multiplied, we add the exponents and keep it the same base of 2. So 2 now to the 8p minus 12 here, plus a negative 4p is equal to 2 to the 4th power. Well, from there, we have our same base again on each side of the equal sign, which is 2. When that happens, our last rule is we can set the exponents equal to each other. So we have an 8p minus a 12 plus a negative 4p is equal to that 4 right here. And now we have to solve for p. I'm going to add a 12 to both sides right here, and I'm going to rewrite this up here so I have a little more room. 8p minus a 4p is just a 4p. The 12 cancels here on the left, and 4 plus 12 is a, well, 16. Divide both sides by 4 to get p by itself, and 16 divided by 4 is a 4. And so after all that, our final answer is p equals 4. I hope this video was helpful for you, and if it was, please subscribe to this YouTube channel and like this video. This helps us make more free math lessons for you and for everyone else. So as always, thanks for watching.
Minute Math, when you need help you use Minute Math.